welcome to our regular scheduled seminar, Wednesday morning seminar. Ross will introduce the speaker, but I want to remind you that this week we have a special seminar on Friday at noon by Michele Calvi talking about reconstruction following the Aquila earthquake in Italy. So remember to show up for that, please. Ross?
Well, I'm very happy to introduce Volkan Sevilgen, who received his master's degree at Istanbul Technical University in 2006, and then joined us as a foreign exchange visitor for 4 years, working with me and helping to manage the Coulomb 3.3 software. So that has about 4,500 users, and there's a great deal of technical support traffic and teaching work that he leads for us. Most recently, Turcotte and Schubert are developing a section in the next edition of Geodynamics that will use Coulomb for classroom exercises, and Volkan has also led the effort to prepare all of that material for Jerry Schubert and to teach Jerry Coulomb, which was quite an experience. In the last 2 years, Volkan has been a USGS contractor. And he's also managed with me a OFDA-funded Balkan seismic hazard assessment project. But 2012 has been Volkan's breakout year, in which he was first author on the paper that he's going to present here today, and third author on Fred Politz's Nature paper on the April 11, 2012 earthquake, which produced aftershocks around the globe. And I think what's wonderful here is that Volkan clearly got an enormous amount of insight and help from Fred, and that generosity coming from a senior scientist, plus watching a young scientist really come into his own is what makes working at the survey great, those kind of collaborations. So I'm very happy to present Volkan to you as he talks about this study, which was just completed.
Thank you, Ross. Well, we are trying to understand whether or not aftershocks or subsequent main shocks are triggered by static stresses or dynamic stresses. Up until recently, we had far better tools to calculate static stresses. And they seem to explain some, but not all of what we see. Very few cases really allow us to distinguish these two. But I'm going to show you the case for the 2004 Sumatra earthquake that we looked at both static and dynamic stresses, and we find that up to the distances of 400 kilometers, the static stresses are not only turning on earthquakes, but also they are turning off earthquakes, and they are changing focal mechanisms. And as far as we can tell, dynamic stress do not do either of these. Here are the main arguments for static and dynamic stresses. Static stresses are imparted by fault slip and are permanent. Dynamic stresses are imparted by seismic waves and are transient. One of the big disagreements between these is the stress shadows. Stress shadows are uniquely attributed to static stress because oscillating seismic waves cannot solely inhibit failures. They are brief bursts of positive and negative stresses. So here how we calculate Coulomb stress or static stresses. Here we first have shear stress. See, the blue area represents we calculate negative stress change, and red areas we think it's going to be promoted. And we add that unclamping stress, some people call it normal stress, and we multiply that with the friction coefficient, and then this is how we obtain Coulomb stress, static Coulomb stress. So Coulomb stress could be very different with different receiver orientation. Receiver means is the fault that we calculate the imparted stress. Here on the left, we are showing north-south strike slip fault. Looks much different than slightly rotated receiver fault to the east. So you notice that one area was in the stress shadows now becomes promoted. It is very hard to hunt for stress shadows because although the volume of the stress triggering and the stress inhibition areas are the same, the seismicity effect is completely different. So you can get 10 times higher number of seismicity in promotion zone, but you can only get down to 0 if you start with one earthquake. So that's why we don't see many cases easily. Stress shadows are also important because we may ourselves be living in a stress shadow. Here are the earthquakes that occurred 75 years preceding the 1906 earthquake. You see many earthquakes. And here are the earthquakes the following 75 years. You see only one. So some argue that the reason that we are seeing far less earthquake is because the stress shadow of the 1906 earthquake. But it is very difficult to resolve this issue with the historical data. So we need a large earthquake with a recent seismicity record. We also need a physically separated receiver fault so we can calculate both static and dynamic stresses and we can compare. And finally, we need long pre and post main shock seismicity records so we can compare the seismicity rate changes. And 2004 Sumatra earthquake fulfills all of these. Here we are in Sumatra region, Myanmar on the north, and you are seeing tip of the Sumatra island on this bottom of the map. And the oblique, so by the way, this is a 1,300 kilometer rupture colored in green. Look how bigger it looks compared to the 8.6 Nias earthquake adjacent to it. It is the largest event ever recorded in 40 years. And that makes it also a very good test case for us. The oblique subduction along the Sunda Trench creates this back arc fault system and creates our ideal test receiver fault. The receiver fault consists of transform sections that we observe strike slip earthquakes, and it also has intervening rift sections that we observe normal focal mechanisms, earthquakes with normal focal mechanisms. Let me plot the earthquakes that occurred preceding the Sumatra earthquake. See how earthquakes illuminates the back arc as well as the rupture. So now let's look at the earthquakes occurred after Sumatra earthquake. Again, you are seeing it illuminates the rupture area, but in the back arc, you start to seeing, especially for some areas, you start seeing more earthquakes, but for some areas, you don't see that many post-main shocks. If you look closer to it, the pictures start to get a little interesting because now it looks like the southern part of the map becomes a little bit more, sustains more seismicity, while the northern part is little, you don't see that many post-main shocks. Let me break this into two figures. So this is the pre-period. So we masked the earthquakes nearby the rupture. And this is the completeness level. These are magnitude 4.5 and above earthquakes being recorded by global catalogs. And this is the after period. Look how different the box N compared to the box S, compared to the box N in two cases, pre and post. And look also how different box S is. By the way, this box N is about 330 kilometers long, so it's not really a small area. So let's find out when the actually shutdown started. So let's look at the time series. So we are looking for the box N. So it just shut down after the earthquake, and it lasted for 5 years. Box S, on the other hand, we are seeing huge increase in the seismicity. It took about 25 years to reach 175 earthquakes, and now we are at 800. Huge increase. And after very same earthquake and two different places. We took all the post-main shock earthquakes, and then we put them into log frequency, log time plot. They decay like aftershocks. And notice that decay in our catalog starts after 3 hours. So this means that whatever happened during the first 3 hours, we don't know, because we don't have that in our catalog. But after 3 hours, what you are seeing is the decay lasts about 5 years. Here's the background. So we have 5 years of shutdown. We have 5 years of rate increase, and they decay in about 5 years. It gets even more interesting. Look at the focal mechanisms preceding. We have about 50-50 strike slip and normal focal mechanisms on the back arc. Look at afterwards. Virtually all the strike slips are gone. So we need to explain why we are seeing this. And this rate turns out highly striking because the rate of strike slip mechanisms drops by 2/3, while rift mechanisms increases by 8-fold. So it's quite remarkable. So let me summarize what we are seeing here in a schematic figure. The transforms are inhibited and the rifts are promoted. So we need to explain this. We first did was we calculated Coulomb stress on the receiver fault. So let me just plot it next to the observation. First two panels on the left are the observation, and the panel on the right is our Coulomb stress calculation. Look, all the transforms are blue or negative or in stress shadow. All the rifts are positive. Some of them are red, some of them are yellow, but they are positive. So what we are seeing here is static stress change explains both stress shadow or seismicity turn off, and also seismicity turn on. We used friction coefficient of 0.4 for this plot, and let's look at all the other friction coefficients. So this is for friction coefficient 0. This is identical to shear stress. We are seeing the same thing. Transforms are blue and rifts are red or yellow. This is the full range of the calculation using different frictions. So our results is consistent if you choose friction lower than 0.5 which seems pretty reasonable if you think that oceanic crust has been shown as a low friction regions by other studies. We also did the same study with using different fault models, but I'm only showing this one. It looks like Coulomb stress can also explain focal mechanism change. Look how the promoted mechanisms increases from 65 to 100. Just think of the pre-2004 mechanisms as a control test. The earthquake hasn't happened during this time, but you are using like a control test only. And all that matters is the number rises afterwards. And this 53% gain in promoted focal mechanisms, in fact, highly significant. And next, we are going to look at the Coulomb, dynamic Coulomb stresses. We used Fred Policy's fault model and his method to calculate dynamic stresses. This is an isotropic Prem model being used for the calculating dynamic stresses. And so we don't have any basin effects or lateral velocity changes whatsoever, etc. So we had to simplify it a little bit. So I'm going to show you an animation that on the left, you will see the transform, dynamic stress resolved on the transforms. And on the right, you will see it's resolved on rifts, on the rifts. Starting. First thing to notice is dynamic stress is sweeping across the fault, and they look rather similar. What different here is the remaining static stresses. And you see the huge directivity. The waves to the north are much higher than waves to the south. We used 6,000 patches, and we ruptured them in succession to create this dynamic rupture model. And we are seeing full waveforms. We are seeing body waves, we are seeing surface waves, and their reflections. All right. And we also calculated peak dynamic stress. The way that we calculated this, we took the maximum positive dynamic stress and we subtracted that. We subtracted static Coulomb stresses, and this is how we get it. First thing you will notice the directivity effect. Look how it is larger to the north than to the south. But what you don't see is any change or any difference between the results for the rifts and the results for the transforms. They look very similar. Remember, we are inhibiting transforms and promoting rifts, but we don't see that in peak dynamic stress results. We also calculated some stress grams. These are not seismograms, but they are stress grams calculated from seismograms. So you are seeing, again, transforms on the left one and the rift one on the right. Again, first thing you notice, Coulomb stress change scale for the stress grams gets increased when you go from from bottom panel to the top, as you expected, and the amplitudes, which means amplitudes get smaller, and the duration gets longer, as you expected. But again, you don't see any difference between transform and the peak, transform and the rift calculation. We also took one junction point from the transform, and just basically the junction of the transform and the rifts, just over there, just right after the largest rift section. Because we want to compare why we are not seeing any difference. So here are the stress grams. So what you notice is stress grams still looks very similar. You can tell the number of positive pulses or number of negative pulses are similar. Duration looks similar. But if you look closer and plot the frequency spectrum, what you see is the transform for the lower frequencies. Transforms, in fact, has higher amplitudes. So this is quite interesting to see because remember, we are inhibiting transforms and triggering rifts. So if anything, this is opposite to what we are observing. All right, so it's going to be brief. I have a lot of supplementary figures, but let me end this with the figure. So what happened, whatever happened during the first 3 hours, we don't know. Perhaps we have some dynamic triggering or whatever. We don't know it. But after 3 hours, the picture is so clear. Static stresses are not only turning on earthquakes, but also they are turning off earthquakes, and they are also changing focal mechanisms. And the dynamic stresses apparently do not do either of these. So if you look at the figure, you are seeing very high amplitude dynamic stresses. Although they are shaking the faults very hard, what matters is, in our study, is the small but permanent static stresses. Thank you.
There are questions for Volkan?
Yeah, that was great, Volkan. I had a question about region S. You showed that it was a 5-year shutdown convincingly for figure N using the time series of events, but for figure S, it wasn't clear if that was for 5 years or something much shorter.
The time series plot.
Yeah. There you go. Well, you first see the jump and then obviously it decays. So it's kind of hard to see how long the decay lasts. But what you are seeing is up until 5 years, you are still seeing some kind of increase. So that's why we are attributing 5 years of increase. It could have been shorter than that, but it looks like.
I guess,
Yeah.
I'm trying to eyeball the slope of the line on both sides.
Yeah, it goes pretty, yeah, it looks like it decays a little bit faster, but if you look at the decay plot, what you are seeing is
Mostly those events.
those are same events in the back arc. So they decay, and these are only the post-main shocks. So they really decay 5 years. So that's why I said they decay 5 years. We don't see any pre-main shocks here. So this is only post-main shock. So that's why I said.
Hi, thanks for the nice talk. I was wondering if you looked at any receiver faults that were in different locations, if there were any viable receiver faults, maybe to the east or west.
For the
I guess
same
I'm
region?
thinking to the east.
For the
I-
same Sumatra region?
I guess the reason I'm asking is all of the faults that you mentioned that have really big changes in seismicity seem to be in the direction of directivity. I was wondering if you saw something different in a region that wasn't shaken up so much by dynamic stresses.
Well, we cannot really place fault on Earth to observe different seismicities. So these are what we got. But what I can tell you that if you look at the peak dynamic stresses, it doesn't seem to control the story here. So, and again, I don't think that's the answer, to be honest with you. But we don't know what happened during this 3-hour period. Perhaps, as you mentioned, during this 3 hours, it's quite possible that actually you might have some dynamically triggered shocks towards north. But we don't see that in our catalog after 3 hours. And these are the global catalogs that using global stations, so it's not dependent on station coverage or whatnot. 4.5 and above, quite hard to miss.
Could you put up the just the first slide that showed the 2004 earthquake and the Nias earthquake? So other people have looked at the seismicity rate change at the site of the future Nias rupture after the 2004 event, and seismicity rate does increase. Actually, one of the most interesting things about this sequence is it has such strong directivity to the north, but there have been no earthquakes that extend further north, and there have been 3 or 4 magnitude 8.5 earthquakes extending the opposite direction. So, so for whatever reason, directivity doesn't seem to play a large role in what gets triggered next here.
Hi, Wayne.
To follow up on this issue of dynamic versus static triggering, person next to me had the same comment about the 3 hours, but he's very retiring and shy, and fortunately someone else raised this. But I guess this is a question directed at Fred. Fred, in your study of the global aftershocks of the 2012 earthquake, you attributed increased rate of magnitude 5.5s to that dynamic triggering from that earthquake. Over what time frame after the earthquake did those dynamically triggered earthquakes occur?
We believe anywhere from 2 days to 10 days. It depends which large earthquake. For the April earthquake, up to 10 days, I think. So that's
Okay.
a lot less than 5 years that we're talking about.
And a lot more than 3 hours,
I have the time.
too,
Yes,
which is,
also more than 3.
yeah. Well, I'll let.
Yeah.
Well, maybe lots of things were triggered in 3 hours, and there wasn't anything. Yeah. Well, I was just going to say impudently, maybe everything was triggered in the first 3 hours, and there was nothing left for the first 10 days. If you're going to, focus in on that, I don't know exactly what. Do you know what was happening in the first 10 days, for example?
Well, I looked at it and I don't see any signal. I don't see any increase. What I did was I just extracted all the earthquakes in my study area, so close to the rupture, and removing also the back arc fault system. and looked at the global global earthquakes, and I looked at from magnitude 4.5, and I don't see any difference 6 days before and after for the Sumatra earthquake.
Maybe,
Dynamic stresses
Because I'm
here are
also the
huge.
one of the co-author of the other paper, so it's kind of ironic
yeah.
that saying one thing for the one paper and another thing for the other paper, but this is what we are seeing here.
Oh, well, that was a very convincing demonstration, so I'll ask a question. That was a very convincing demonstration, so I'll ask a question
Thank
on
you.
another area. But why, say, the Parkfield earthquake? A large number of aftershocks, a very large number, occur right along the length of the fault in a stress drop area. Why is that?
Well, I think, do we know the focal mechanisms of these earthquakes?
Well, I'm thinking of the Parkfield, yes, we know it. We don't know the orientation of the receiver faults.
Well, I can show you one example from Parkfield area. The creeping
Perhaps I'm
section.
taking this too far afield. If you have it, that you don't have an immediate answer for that. That if is it stress triggering or what?
Well, the answer, I don't know.
Oh,
Because
that's fine. That's one other comment I wanted to make. Why do you persist in using bars when you should use megapascals?
well, it's very practical way, because we are living under 1 bar atmospheric pressure, and we put about 3 bars to our car tires. Do you know how much MPG or MPA do you put on your car tire, or what? It's harder, right? And the plus, the another amazing thing is, it's been shown that other stress triggering studies, about 0.1 bar is adequate to trigger earthquake. When you convert that to MPA, the number gets so small, so it doesn't really, it almost looks like 0. So that's a like psychological effect.
Oh.
Okay, I know 100 miles to Sacramento. I don't know in kilometers right off. Should we then not go to
Well,
the
now
metric
you are
system?
feeling me because I'm from Europe, so it's completely opposite.
Okay, I have to take the mic away from Jim. Let me just offer my answer to your question. Why do we see aftershocks on the fault plane if that's the deepest stress shadow? And the best answer is that there's a lot of spikiness and variability to the slip. So unless the slip is very smooth, there will be patches of stress drop along the fault. And that's probably the principal reason. And the second reason is the one you mentioned, that the fault itself is not perfectly straight. Some of those shocks have slightly different orientations, and that can also contribute to it. So where we have very good variable slip models for the fault, there is often, and Parkfield is one of those, a fairly good correspondence between where aftershocks occur and where stresses are calculated to have been raised.
And I also want to add one comment about that. That's the reason that we are trying to hunt for faults are physically separated by several hundred kilometers, because we don't know the fault rupture that exact that we can tell the earthquakes, why these earthquakes occurring. So when you get farther from it, the details of the rupture becomes negligible. So then your results become more robust. So that's why it's so important to do this study in Sumatra rather than Parkfield, because I'm sure a lot of people has different rupture model for Parkfield, and they would contradict. You can't get anything from that in terms of resolving the issue or like contributing the debate. So that's
One comment on dynamic triggering. The most compelling evidence for dynamic triggering is prompt onset as the dynamic waves go past. Almost all of the clear examples involve that. There is the issue of delayed triggering, and we see some evidence that that happens, but of course, the longer the delay, the more dubious the association, the causal link. So it's quite possible, quite likely in my mind, that in the first 3 hours there was a bunch of dynamic triggering going on
it's possible.
that you just don't have in
It's absolutely
Yeah.
possible. So that's why I mentioned that
Yeah.
we also calculate completeness, magnitude of completeness, and the results that I'm showing is all above completeness. We did it for time series, but I completely agree with you. If anything happened during these 3 hours, we don't know.
This might be a good study for Xi Jinping to do, to try
Yeah.
and see those early aftershocks by this kind of template
Yeah.
waveform matching method, because I had the same issue that I wanted to ask Dave about. It
I think
seems
so
like the
too.
dynamic triggering occurs when the dynamic waves pass.
Yeah. The only problem is we don't have that many stations in Indonesia. So
Yeah.
it's, and plus you are still kind of close to the fault. So it's really hard to be thought about that. We've been doing this for like 4 years, right, Ross? We've been doing this for 4 years. We looked at that possibility too. But it's really hard to filter waveform while you are relatively closer to the fault, the actual source fault. What Jigan does is, there's an earthquake half world away, and your station is just next to you. So when you filter the low waves, you are seeing the local triggered events. But you can't see this because they're going to be buried. It would be hard.
You know, just to continue this discussion, of course, in Fred's paper, almost none of these supposedly globally triggered events that we find are triggered immediately. They're all delayed. So it's not clear that yes, there is evidence for dynamic triggering that's immediate. Almost in every one of those cases, they're extremely small earthquakes. In the Parsons and Velasco study of global dynamic triggering of magnitude 7 main shocks, they all take place in the first few hours, and they're extremely small. When Tom looked at triggering of magnitude 5 and larger during the passage of the waves, he found nothing. So the evidence seemed to suggest that dynamic triggering tends to be delayed, particularly if we're going to consider the earthquakes that matter to us in terms of hazards. So it makes it very, very difficult to tease one effect from another.
Immediately raises the question of why.
Yes,
Yeah.
exactly. Why is there a delay? You know, it's not clear. Is there some kind of damage, some kind of change in fault cohesion that happens when the waves come through? In addition to whatever they do to the Coulomb stress, there may be, you know, fluid motions that get triggered. I think it's an utterly open question and an interesting one.
Tom.
Here.
Yeah, Volkan, that's certainly a very interesting and provocative talk. Could you go back to the aftershock slide and
You
tell
mean
me?
the decay?
Yeah, decay.
All right.
And tell me what the spikes are.
Tell what they are?
The spikes are.
This month?
Yeah, so you got 3 gray spikes there.
Those are the aftershocks of an aftershock.
Yeah, well, these are increasing the rates of earthquakes by 3 and 4 orders of magnitude. So can you tell me what magnitudes those earthquakes are, or where are they, or how close?
Well, there are areas that we see swarms on the back arc. Perhaps they are related to that effect. Because I agree with you, if we have that many earthquakes, we should have had very large earthquake on the back arc, right? Because we can only have that many aftershocks, these lines, the lined up thing.
Okay, so each point is a day?
That's the inter-event time.
I mean, I realize it's logarithmic, so each point's a day.
No.
So these things last
These are
for some period of time
Well-
then at these very elevated rates, right?
So each point in this plot is the time between earthquakes. So
Time-
you first, what you do is, I thought this would be a standard figure, but what happened is, you take the time difference between each earthquake. So that's your inter-event time, right? So then you start from, you sort them out, and you actually, what you are seeing is, you don't sort them out, but what you are doing is, each of them actually the time between earthquakes. So the first earthquake,
Okay,
So
all
we-
right.
so times in day.
In
So-
days minus one.
Yeah,
Yeah.
1 over the time between, 1 over the time.
So this is not a bunch of earthquakes in so many days. This is the reciprocal of the inter-event time.
Sure.
Well, still in all, because that number becomes very large, it's still true that the rates of earthquakes jumps considerably, just simply
Yes.
because the inter-event time becomes so small.
And you can see it in after, let's say,
Okay.
I understand what you are getting at. So you are seeing is about 1.5 day, you are seeing some burst of seismicity.
Well, it could be more than that because it's log time there. So, you know, when you're out at,
Well, the log time is
you know,
at
hundreds,
bottom,
when
so-
you're out at the two of the largest ones, you're between 100 and 1,000 days. You know, those things could be lasting for a couple hundred days, couldn't they?
No, that's the day.
It's not a histogram as a function of log time. It's in our judgment, a better way to look at this phenomenon. If he had declustered it, you wouldn't see
You have the
anything
microphone.
but the trend. If he had declustered the catalog, all of those spikes would have gone away.
Yeah.
And you'd have just seen an Amori decay along that line. But since he left everything in there, like you would see on any ETAS simulation, you get spikes. You get aftershocks of aftershocks or swarms in this case.
But
and they
still,
fly up.
still in all, on the abscissa, you know, when you go out to 1,000 days or you know, 10 to the third days, maybe all those dots are occurring on a single day, but you know, given that you move just a little bit, you know, and that's weeks or months all by itself, because it's log time out there.
Yeah. But they
So you're
don't,
going to 100 to 200 days.
that's
and-
true.
Right, so.
Yeah, it's about, let's say, 30 days, I would say, because between 1 day.
But at any rate, there's swarms, and are they swarms on what, the transforms or the ridge segments?
On the rift section.
On the ridge segments.
Because transforms, you don't see any earthquake. Most of the transforms, you don't see any earthquake.
Well, in the south, you did. I mean, the northern transforms, they shut down, but the ones to the south, didn't you have red colors for the ones
That's
to
true.
the south?
That's true, for the
Yeah.
southern part.
So the
south.
southern transforms did have increased seismicity. It was the northern transforms that didn't.
Correct.
Okay.
Actually, let me show you the clustering, because we also declustered the catalog. So here's what happens. So this is completely declustered catalog with using Gardner and Napoff. So look at the box N. You still see the shutdown. And this time, the clustering actually works quite well. So you don't see any rate increase or decrease on the box S. So that's why we, after we are seeing this, we are thinking all the dots that you are mentioning would be eliminated because they are aftershocks of an aftershock.
No, your plot was a very interesting way of presenting the data. I just was a little bit confused as to what was really going
sorry.
on, because I hadn't seen anything like that before.
Thank you.
Other questions? Was there a question? Yeah.
Yeah, first of all, I'm just an interested observer, not a seismologist, but my question is directed at Fred and your triggered earthquakes from the April 12th event.
You might
You said it took up to 10 days for some of those to occur.
Today,
And since you're saying they're dynamically triggered, what exactly is moving for 10 days to do that?
Well, nothing's moving for 10 days. Yeah, sorry. Yeah, the free oscillations and so forth have settled down by then. But Ross gave us a nice explanation before. There are different theories, all of them fairly speculative as to what could cause a delayed dynamic triggering effect. So you could trigger small ruptures that cascade into larger ruptures, which has been suggested by David Shelley and others, or you could jump around fluid barriers, open up fluid barriers, and that gets fluids into the parts of the faults that are likely to fail, and that's a process that also takes time. And there's other ideas as well that Tom Parsons has put out.
Thank you.
Okay.
Volkan, you say that static stress changes can change the focal mechanisms, but what you showed is not that at a given point the mechanism changed before the earthquake as opposed to after. What you showed is that the number of focal mechanisms of one type decreases just because you shut off those faults. So just be careful maybe with the wording.
I agree with you. It could be worded a little differently, as you suggested.
Any others? Well, thank you, Volkan, for a very
Thank you.
stimulating talk.
Thank you.
And I suppose,
And long live bars.
and don't forget that Friday we have a seminar at noon.